All right, we're back. I want to talk a little bit more, and I'm getting us towards the conversation about buffers, and so we want to talk about equilibrium. One of the ways I like to talk about equilibrium is I like to kind of start with a physical equilibrium, and so I like to talk about, let's just say we have an Erlenmeyer flask that's been sitting on my desk for a long time, and I think in the course of this quarter, I've probably shown you this little flask or a little jar of water that sits on my desk. So I actually have done this. Okay. So we're going to stopper that flask. So we're going to make this a closed system. And in that flask, we're going to have a bunch of water down here in the liquid phase. And we're going to leave this for a really long period of time. And then we might be cognizant of the fact that if we were to look at this water and observe it through the course of the quarter, that we might see that the level stays constant. Now, that might be interesting, and what you want to think, though, is that the system is what we'll call dynamic, that there is something happening in there. It just happens to be on a level that's not visible, I suppose, to the eye. So let's think about that for a second. So we've got this liquid water down in here, and you may remember this concept of vapor pressure, that above every liquid in a closed system, that there's going to be a bit of that liquid above the liquid form. There's going to be a little bit of gas of that. So if we think about that, we've got these particles of water vapor above it, and those water particles would be in the gas phase. Now, if we look at this system, we might understand, because it stays constant, that this this level of water is going into gas, and that gas is actually condensing into liquid, and that might be a system at equilibrium. Okay, so that's a physical system, but it gives us something to talk about when we start talking about equilibrium. A couple of things. I'm going to draw the water in the liquid phase really big, indicating that there's more of it in the system. I'm going to draw the forward reaction, that would be evaporation, and I'm going to write the reverse reaction, which would be condensation. And I'm going to write the water in the vapor form, just small, because what I'm getting at is there's less water in the system in the gas phase than there is in the liquid phase. So the key point about an equilibrium is that the forward reaction and the reverse reaction are equal, okay? But the amount of product and the amount of reactant don't necessarily have to be the same. Let's say that again. They don't have to be equal, but they have to remain constant. And that's the big key, okay? So this is a physical equilibrium. And what I like to try to get students to think about is what's equal, and the equal is the forward reaction is equal to the reverse reaction, and that's what makes the system stay constant, right? And yet it's dynamic, because this is happening and this is happening. So these particles are not constantly the same particles all quarter. Those particles sometimes are down here, and then sometimes they're up here, because this is a dynamic system. What stays the same? This is the amount of the reactant and the amount of the product. And that is kind of what it means to have a system at equilibrium. Now, when we talk about a weak acid system, that vinegar, COOH, and water, and we look at that system, that's a chemical equilibrium where the hydrogen is being donated and making hydronium. And then we have this acetate ion over here. And so what we're getting at here is, here are the reactants and here are the products. The amount of these stays constant. The rate at which the acid gives the water its proton is equal to the rate at which the hydronium gives its hydron to the acetate and goes the opposite direction. So this is a chemical equilibrium. This would be a physical equilibrium where we're looking at a phase change. This is a chemical equilibrium. And that is a really, really big concept to try to understand. Okay, when we quantify equilibrium, we give it a K value, and I'm not going to dwell on this too much. We talk about the amount of products, over the amount of reactants. That's kind of how we've decided we're going to do that. And they're going to be raised to the power of their coefficients. And this is a way for us to quantify equilibrium and to give it a number. Okay, so let's look at that for a second. When we talk about K values, I'm going to go over here and we're going to look at a reaction. When we look at a reaction like this, okay, and we have the system at equilibrium, and we want to put the concentration of the products, the H3O plus, that's one product, and we're going to multiply that by the concentration of the other product. You'll notice it's added in the equation, but in the equilibrium expression or constant, it's multiplied. And then we're going to put that just over the HBr, and we're going to leave out the water, and that's because the concentration of water can't change, right? The concentration of water can't change. And we know this as an equilibrium constant, okay? So that one is easier. A couple things there that we have to leave out, so we don't have the water there. We have a multiplication rather than an addition. That's kind of confusing to students, but that's just the way they've decided to do it. So then when we look at the second expression, KEQ for this second reaction, we're going to put the products over the reactants. And this time we get to use the second part of this idea where we're going to put the 2 here. We're going to use the coefficient on this balanced equation as the exponent in the equilibrium expression. So what this allows us to do is quantify or make a number out of this equilibrium. So we can tell a little bit about it, okay? So what the K value does is if you think about a large K value, okay, K is large, and that just means bigger than 1, okay? It means that you're going to have more products in the equilibrium than reactants. Okay, so your reaction might look like this. You'll have reactants in equilibrium and you'll have a lot of products. It's almost like we favor, this favors the products. Okay, a small k, a little k, would imply that you have very few products and lots of reactants, right? So this says we're going to say this one favors reactants. You could also maybe say that this equilibrium doesn't go as well. The reactants are hard to get together to make the product. And we might look at that equilibrium like this, just to kind of show it to you super symbolically. Okay, so the value of K, there goes my parents' clock. It's halfway to 9. What does this large K mean? Well, it tells us the sort of nature of the equilibrium. A large K, favors the products, right? And a small k is going to tell us the nature of this equilibrium favors the reactants over the products. So when we look at that equilibrium, and if we think about it like the water, this would have a large K or a small k. So if I put, a little bit of water, not in the gas form, over a lot of water in the liquid form, you might remember that if you have a denominator or fraction that's larger than the numerator, this is going to be a small k. So this would be a way to quantify the equilibrium. Okay, so a large K favors a reaction. That's one way to think about it. Okay, so I'm going to leave it at that. That I think that's good for that. I want to talk about Le Chatelier's principle, and before we do that, we kind of have to talk about a rate of reaction. So when we think about a rate of a reaction, we know that there are some reactions that are slow, like the decomposition of your leftovers that you leave in your refrigerator for a long time. And we know there are some reactions that are really fast, like that magnesium that reacted with hydrochloric acid, right, and gave us that magnesium chloride and water, right? Another slow reaction might be iron reacting with oxygen to form rust. That doesn't happen very quickly, right? So rates of reactions are determined by a couple of things: concentration, temperature, pressure, and catalysts. Okay, and we'll talk a little bit about what a catalyst is, right? A catalyst essentially is going to take a chemical reaction and lower the activation energy barrier, right? So when we looked at those reactions where we had the activation energy and then the products, we had that's an exothermic reaction. We have an endothermic reaction where we have the reactants and we have the products, right? Reactants, products, activation energy, transition state, right? Reactants, products, activation energy, transition state. Well, when I introduce a catalyst to the situation, what I'm going to do is lower the activation energy barrier and make this reaction easier to accomplish. So I'm going to lower the hump that this system has to get over, and now it only has to get over that much energy, or in this case, that much energy to get from reactants to products. Okay, so having said that, now we can talk about Le Chatelier's principle. And basically, Le Chatelier's principle says that a system at equilibrium will shift, let me erase that, I'm trying to talk and write, will shift to relieve a stress applied. Okay, so what that means is if we take the system at equilibrium, this system right here, and all of a sudden we chill the room down or we heat the room up, we can actually get this physical equilibrium to change, right? If we chilled it down, you might see that those gas particles might condense, and I might have the water level go up a little bit because those particles are going slower and they're going to condense into liquid rather than be gas. Contrary, if I heat these up, you might think about these particles going more into the gas form, and so this water level might go down if I change the temperature at which this is sitting, right? Same thing happens here. If I have a chemical reaction that's happening, I can do things to this chemical reaction to cause the equilibrium to shift, okay? A little different than a physical equilibrium, but very similar, okay? The reaction that you saw with Scott was you had iron and thiocyanate that formed that iron thiocyanate ion. And we said this one was blood red, this one was clear, and this one was rust colored. And what we did in this case is we basically, we added iron to the situation. And by adding that iron, if you think about the fact that these things have to collide, these particles must collide in order to react, right? Basically, the more I add, the more collisions are going to happen. I'm going to increase the forward reaction, and that's going to lead to an increase in the iron thiocyanate, and that's why that solution went blood red. It got darker. When Scott added silver to this solution, you saw that the silver and the thiocyanate ion connected to each other, and it lowered the concentration of the thiocyanate, and basically now the iron has less thiocyanate to react with, and so that led to this forward reaction actually slowing down and that reverse reaction staying exactly the same. And so you saw the equilibrium shift in quotes over and get sort of clearer, right? And you actually saw that equilibrium shift. And this is what Le Chatelier's principle says, okay? So it's all about collisions. So basically we have to think about collisions between the particles, right? It's all about the concentration, the temperature, the pressure, and catalyst. So we're just going to walk through those very quickly. So it turns out that if you increase the concentration, right, it's going to cause the reaction to go faster. And that's going to shift the reaction away from what you shifts away from what you're adding. Okay. The opposite's going to happen if you decrease the concentration, and we saw that with the concentration. That's going to cause the reaction to slow down, and it's going to shift, the system is going to shift towards what you removed. Okay, so that's what we saw again when we we added the iron, and we saw the solution shift in this direction because the forward reaction increased. It used up the excess iron, and it shifted or favored the products. When we removed the thiocyanate, we took it down. The forward reaction slowed down because there are fewer particles to collide, and so the equilibrium shifts to replace what you've removed. So that's kind of what happens with pressure. With temperature, you saw that Scott said that there was heat involved in this reaction, and when we heated this solution, because we added heat to the system, that causes the reverse reaction to happen faster than the forward reaction for a brief time, and the equilibrium shifted and got more clear, and we were able to ascertain that that was an exothermic reaction. So heat or temperature acts much like concentration. So if I increase the temp, it's going to shift away from it, right, just like this one. And if I decrease the temp, it's going to shift towards it, just like concentration. So those kind of act the same. So equilibrium is just a manifestation of, what's happening. Is the forward reaction increasing? Is the reverse reaction increasing? Because what we do is we disturb this equal forward and reverse reaction for a brief period of time. And then it just reconfigures itself to equilibrium. Okay, now pressure is interesting when we think about a system of gases, okay? It turns out that gases have to do with the space that they take up. So I'm going to go ahead and look at an example of this. So for this example right here, I have hydrogen gas reacting with iodine gas, and I'm getting this hydrogen iodide. And when I think about this gas, there are 2 moles of gas on this side and 2 moles of gas on this side, looking at those coefficients. And so we know when we think about a mole of gas, it's going to occupy a certain amount of space, right? Okay. And that basically means that if I increase the pressure on this equilibrium right here, what's interesting about that is this side of the equilibrium occupies 2 moles of gas, and this side does too. And so if I increase the pressure on this gaseous equilibrium, it's not going to shift any direction because both sides occupy the same volume, because we know that gases occupy a certain space. That goes back to our gas laws, right? So in this situation right here, however, because I have this equilibrium, this is 1 mole of gas and 1 mole of gas and 1 mole of gas. But if I increase the pressure on this system, okay, which side of this is going to occupy more space? So if we think about when we increase the pressure, right, we go back to that piston system that we have, right? If we increase the pressure, we're pushing down on this, we're increasing the pressure. That means we're decreasing the volume. And so it's almost like this equilibrium squirts out to the side of less volume. And it turns out that this side is going to be less volume. Okay, so when I think about this, the collisions, as I increase the pressure, I decrease the volume, these particles are going to collide more often. The forward reaction is going to increase, and that's going to shift the equilibrium to the side of the equilibrium with less amount of gas. And it just is a manifestation of these particles colliding. The opposite's going to be true if I decrease the pressure. So if I decrease the pressure, I'm going to increase the volume, right? And basically that means that now this gas can expand out. Another way to think about that is, as I give these 2 particles right here more space, it's less likely that they're going to collide with one another, and therefore they are going to, the forward reaction is going to slow down. And so this is actually going to shift the equilibrium to the side with more gas. So long story short, pressure only applies to gases, okay? And if you increase the pressure, right, it's going to be, you're going to go to the side with fewer moles of gas, okay? And if you decrease the pressure, the opposite's going to happen. It's going to go to the side with more moles of gas. And it all goes back to collisions, right? We always kind of go back to collisions. And so the last piece of this is the catalyst. And basically, if I add a catalyst to an equilibrium, right, it's not going to shift the equilibrium because the forward reaction is going to be affected just as the reverse reaction. So if this is the forward reaction and I've added a catalyst, it's going to be easier to go, right? But so is the reverse reaction. So we have the reactants going to products, but this is just going to happen faster because we've lowered the activation energy barrier. So there's going to be no shift in the equilibrium. There's no side it prefers. It's just going to make these go faster because it lowers the activation energy. Okay, so let's play with that for a second. I want to kind of go through a couple of examples. Let's do this one. I think this is the most, there's enough here to work with. Hopefully the concept gets clear. So let's go here and look at all this. I'm going to erase this so we have space. Okay, so this is an exothermic reaction. So we have C2H4 plus Cl2. These are all gases. And it's C2H4Cl2 plus heat. This is exothermic. Okay, so this one asks if we increase the concentration of this substance right here. So we're going to take this substance and increase it. Okay, going back to the collision theory, these particles are going to collide more often. So we have more collisions. And that's going to increase the forward reaction, which means it's going to shift to the product side. Because what actually happens is the forward reaction goes faster, the reverse reaction kind of stays the same, and you have this inequivalency, you have this non-equal situation, and so you're going to produce more products faster than the products go back to the reaction, or the reactants. So just remember, as we increase something, the equilibrium is always going to shift away from it. So we've increased this, so it's going to shift away to try to use up what you've added. And the opposite's true for decreasing. So I'm going to take this chlorine gas, rewrite this equation. Okay, so I'm going to decrease the amount of the chlorine gas. What that does is now these two particles can't collide as often because there's not as many. That's going to slow the forward reaction down but keep the reverse reaction faster. And so this imbalance in the reaction basically is going to cause the equilibrium to shift, because this imbalance, it's going to make products are going to make reactants faster than reactants are making products. And so we have the equilibrium shift to the reactant side. So it's going to shift to the products, to the reactants. And my sort of cheat to this is, since I've removed Cl2, removing Cl2, it's going to try to shift over to replace what you've taken out. Okay, let's go to pressure. If we decrease the pressure, we have to go back and look at the moles of gas, right? 1, 1, and 1. So this side has 2 moles, and this side has 1 mole. So when I decrease the pressure, think piston here, decrease the pressure. So we're raising this up, right? That means more volume. And so it's going to take the side, it's going to go to the side with more moles of gas. Now, a caveat to that is if you have an equilibrium that has no gases, then when you change the pressure, it's not going to change the equilibrium at all. Okay, so again, this has to go back to our gas laws just a little bit. Volume and pressure and moles of gas relating to one another. Okay, let's talk temp for a second. Thinking about temperature as energy, thinking about temperature as heat, which perpetuates that misconception. But basically, if I increase the temperature, if I increase the temperature of this, that's going to cause the reverse reaction to speed up. So I've got my forward reaction going along, my reverse reaction is going to happen faster because I've added more product. And it's going to shift away to try to use up what you've added. So this is actually going to shift, this right here is going to shift to the reactant side. So the name of the game here is just kind of contemplating what is being added, what is being removed, and which reaction forward or reverse are going to increase. And then that imbalance is going to shift you one way or it's going to shift you the other way, depending. Again, and it has to do with, if the reverse reaction is faster than the forward, we're going to have reactants build up faster, right? Because the products are being used up. And so that is your concept of equilibrium. Going back to just the constant and the K value, basically when we have those concentrations at equilibrium and we have the equilibrium expression, So in this one, we wrote it earlier, I think. It was right here, right? When we write that equilibrium expression and then they give us our concentrations at equilibrium, okay, so we'll plug those in. The H2 is 0.98. The I2 is 0.78. Oops, did I do that right? Did I write that right? I guess I didn't, but that's okay. 0.78. And then this substance right here is 0.21. Okay, we're going to go back and do that one again. So let's write that one. K is equal to HI squared over H2. It's a good thing I rewrote this because it's not the same equation. We plug in the values. H2 is 0.95. I2 is 0.78. HI is 0.27 squared. When I do that math very quickly, point 0.27 squared divided by come on, calculator, do your thing. Okay, let's try that. Clear. Okay, 0.27 squared divided by 0.95 times 0.78. And I get 0.098. Basically, this is a small K value. And so what this is going to tell us, a small K value tells us it's going to favor products. So we're going to have more products in this equilibrium than this one. So we're going to have more of these, because this, I lied, totally lied. We're going to have more reactants than products. So we're going to have, and if you look at it, that's exactly what it says, right? There's more hydrogen, there's more iodine in this solution than there is hydrogen iodide. So this one favors, that small K value favors reactants. Okay, I guess when you fly and you travel and you talk, you get kind of tired. So there you go. All right. So I'm going to leave that there. We'll hold that off. And I think what I'm going to do is I think I'm going to rest and I'm going to come back to you guys and get the last 2 lectures up tomorrow. Thanks for listening.